In this video, we will be looking at electrophilic addition reactions of alkenes, focusing on reaction of alkenes with HX. In an electrophilic addition reaction, an alkene acts as a nucleophile reacting with some species that is an electrophile. The overall change in the reaction, we have our alkene connected to whatever groups, and it'll react with some other species. So it'll still be connected to the same 4 groups originally, but it will also be connected to A and B. We can see that this is overall an addition reaction because AB is adding to the alkene, giving a new molecule. As we talk about some examples, we will see why it's called electrophilic addition. Now, why will this reaction occur? One thing is to consider bond breaking and bond forming. So we have our alkene, we have AB, and then it is reacting to form this product. And I'm only drawing the bonds that matter right now. So for this reaction to occur, we are breaking a pi bond, and we are breaking a sigma bond. But we are forming 2 sigma bonds. Sigma bonds are stronger than pi bonds, so here we have to break a sigma, we form a sigma, but here we break a pi and we gain another sigma. So overall, this product is going to be more stable. In other words, thinking about our starting material compared to our final product, we can see that this reaction will be spontaneous. Another way to think about electrophilic addition reactions is to consider a Lewis acid and Lewis base. So a Lewis base, this is a nucleophile, and a Lewis acid, this is an electrophile. So because the alkene has very exposed electrons, it is attractive to an electrophile, and it can be attracted to an electrophile. So the alkene acts as a nucleophile and shares electrons with an electrophile. So here we have an electrostatic potential map. Again, blue is positive, red is negative, and we have a lot of electron density above and below the plane that contains the alkene carbons. Now, if we have a species that has positive character, then the alkene can share electrons with the electrophilic atom. So the alkene acts as the nucleophile, sharing electrons with an electrophile. The first type of electrophilic addition we'll be looking at is reaction of an alkene with HX. So here we have a few examples. If we have cyclohexene and we treat it with HI, we can add H and I across the double bond, so we no longer have an alkene, but we now have an alkyl iodide. If we carry out this reaction using HBr, we add H and Br across the double bond, giving an alkyl bromide. If we use HCl, we add H and Cl across the double bond, giving us an alkyl chloride. And finally, if we tried this reaction with HF, we really get no reaction. So overall, in terms of reactivity, the first reaction with HI, this is going to be the fastest. This is slower. This is even slower. And this is so slow that it essentially doesn't even occur. So we will not worry about this reaction. We can think about these 3. Over here we have a few more examples. Ethylene or ethene can react with HBr to form ethyl bromide. 1-butene can react with HBr to form this product, 2-bromobutane, and this product, 1-bromobutane. but this product is obtained as the major product. And in our third example, this alkene can react with HBr to give some of this, very, very small amount of this, and we actually get some of this as well. So just looking at a few examples, let's think about the experimental evidence that we have so far. HI is more reactive than HBr, more reactive than HCl, more reactive than HF. If we have an unsymmetric alkene where the hydrogen could add here and the bromine here, giving this product, or the hydrogen becomes connected here, the bromine becomes connected here, giving this product, there is apparently a preference. So the hydrogen adds to the carbon that starts out with more hydrogens, and the bromine adds to the carbon that starts out with fewer hydrogens. So there is a regioselectivity in this reaction. And finally, if we look at this example, we have the same situation with regioselectivity, similar to what we saw up here, but we also have a different arrangement of atoms where the bromine became connected to a carbon that didn't have the alkene. So what does this experimental evidence tell us about the reaction mechanism? Let's take a look at the electrophilic addition of HBr to ethylene. So we know that the alkene is electron rich, and if we think about HBr, we need to keep in mind that bromine is more electronegative than hydrogen, so bromine has a partial negative and hydrogen has a partial positive. So the hydrogen is our electrophilic atom. The alkene can act as the nucleophile. In other words, the pi electrons can be shared with the hydrogen, pushing these electrons onto the bromine. What that gives us, so this carbon is still connected to the hydrogens, still connected by the sigma bond to the other carbon. This is the pair of electrons that used to be the pi electrons, and we are left with a carbocation. We also have bromine, where this pair of electrons is what used to be shared between the hydrogen and the bromine. And this has a negative charge. Now we have a carbocation. Now this is our electrophile, and this is our nucleophile. So the bromine can act as the nucleophile, sharing its electrons with the carbon. And that gives us this product. So we have a new bond between the carbon and the hydrogen. The electrons that make up that bond used to be the pi electrons. We have a new bond between carbon and bromine. The electrons that make up this bond would be one of the lone pairs from the bromine. Keep in mind, we can never prove a mechanism. We can disprove a mechanism. We can gain experimental evidence that supports a proposed mechanism, but we cannot prove a mechanism. So now that we have a proposed mechanism, we should consider whether this is consistent with the experimental evidence we have so far. As we look at this proposed mechanism, we need to think about what is likely to be the rate determining step. This proceeds in two elementary steps. Here we have something with negative character sharing electrons with something with positive character. That's probably going to be a relatively straightforward, a relatively easy reaction. But in the first step, this is where we are forming a carbocation. In particular, here we have a primary carbocation. We know that's going to be really, really hard to form. So the first step must be the rate determining step. What's happening in the rate determining step? The alkene is sharing electrons with the H of HX. Recall the relative reactivity of HX. HI is more reactive than HBr, is more reactive than HCl, is more reactive than HF. This trend in reactivity makes sense if this is the rate determining step, because the HI bond is going to be easier to break, and so this reaction can happen faster compared to reaction with HBr. HI is easiest to break, HBr a little bit harder, HCl a little bit harder, HF even harder to break. So the reactivity directly parallels the relative acidity of these compounds, because that's really what we're looking at. We say that this acts as a nucleophile. We could also think of it from the perspective that this is acting as a base grabbing off a proton. And so the relative acidity is going to be the same as the relative reactivity with an alkene. Let's look at a few examples and try to determine whether the proposed mechanism can account for the observed regioselectivity. So if we react 1-butene with HBr, the product that is obtained is 2-bromobutane, not 1-bromobutane. If we react 2-methylpropene with HCl, the product isolated is 2-methyl-2-chloropropane, not 1-chloro-2-methylpropane. And if we react 1-methylcyclohexene with HBr, the major product is 1-bromo-1-methylcyclohexane, not 1-bromo-2-methylcyclohexane. This particular regioselectivity was observed by Markovnikov, who summarized the observations in what's now known as Markovnikov's rule. So the way to think about this is that if we have an unsymmetrical alkene, then the hydrogen adds to the carbon that started out with more hydrogens, and then X adds to the alkene carbon with fewer hydrogens. So looking at this first example, this alkene carbon has 1 hydrogen, this one has 2 hydrogens. The alkene carbon that has more hydrogens is the one that gets the extra hydrogen. The alkene carbon that has fewer hydrogens is the one that gets the bromine. Over here, this carbon has no hydrogens, this carbon has 2, and so hydrogen adds to this carbon, giving a CH3. The chlorine adds to this carbon. And finally, in this case, we have no hydrogens. Here we have 1 hydrogen. So the hydrogen becomes connected to this carbon, and the bromine becomes connected to this carbon. But this is just an empirical rule. This doesn't explain why it happens. It just explains what happens. Let's try to figure out why. So why is Markovnikov addition observed? Why is it that the hydrogen becomes connected to the alkene carbon that had more hydrogens, and the bromine becomes connected to the alkene carbon that had fewer hydrogens? Think about the reaction mechanism where the alkene shares its electrons with the hydrogen. Either we can think about this as a door and this is the hinge. These electrons move out so that this becomes connected to the hydrogen, or this could be the hinge and the door opens this way, grabbing the hydrogen, becoming connected to this carbon. So in other words, there are 2 possible carbocation intermediates. If the carbon on the left is the one that remains connected to the electrons and becomes connected to the hydrogen, we get this, so that this is our carbocation intermediate. Or if this carbon is the one that becomes connected to the hydrogen, then we have an extra hydrogen here, and that leaves this as the carbocation. Let's do the same thing here. If this carbon is the one that grabs the hydrogen, then this is our carbocation, right? Because this carbon's connected to an extra hydrogen. If this is the carbon that grabs the hydrogen, then here's our extra hydrogen, and this is our carbocation. Finally, if this carbon is the one that grabs the hydrogen, here's our extra hydrogen, and this is our carbocation. If this is the carbon that grabs the proton, then our extra hydrogen is connected here, and this is our carbocation. So because all of these alkenes are unsymmetrical, either alkene carbon could become connected to the hydrogen, resulting in two different carbocations. Now, looking at each pair of carbocations, let's identify the more stable carbocation. This carbocation is on a carbon that's connected to only one other carbon, so this is a primary carbocation. Here the positive charge is on this carbon that's connected to two carbons, so this is a secondary carbocation. Secondary carbocations are more stable than primary carbocations. Here we're looking at a primary carbocation compared to a tertiary carbocation. Tertiary carbocations are more stable. Here we have a secondary carbocation compared to a tertiary carbocation. Tertiary carbocations are more stable. Focusing on the more stable carbocation, remember the second step, according to the mechanism, is where X minus adds to the carbocation. So if bromine adds to the red carbocation, then we get this. That is the observed product. In our second example, if chlorine adds to the blue carbocation, we get this product, and that's what was observed experimentally. In our third example, if Br minus adds to the blue carbocation, that would give us this, and that is also the observed product. In other words, we get Markovnikov addition where the hydrogen becomes connected to the alkene carbon that was originally connected to more hydrogens, and the X becomes connected to the alkene carbon that was originally connected to fewer hydrogens, because adding the hydrogen to this carbon leads to the more stable carbocation. So Markovnikov addition occurs because it proceeds through the more stable carbocation. Let's revisit what we learned earlier about carbocation stability and Hammond's postulate and see how this applies to electrophilic addition. This product arises through a tertiary carbocation, and this product arises through a primary carbocation. In terms of energy, let's say this is our starting material, and that's the same on both of these. And let's say this is our tertiary carbocation. Well, we know that our primary carbocation is going to be much higher in energy. So in terms of carbocation stability, a primary carbocation is higher in energy than a tertiary carbocation. Now remember, Hammond's postulate tells us that if you have two states that are similar in energy, they will be similar in structure. So if we were to fill out this reaction progress, up here we have our transition state. The transition state is more similar in energy to the carbocation than it is to the starting material. So whatever we know about our carbocation intermediate, that gives us information about our transition state. So because a tertiary carbocation is more stable than a primary, the transition state leading to it, which we can think of it as kind of like a tertiary carbocation. Over here, our transition state, this is going to be kind of like a primary carbocation. So because of Hammond's postulate, we know that this transition state is going to be higher in energy than this transition state because we know that this intermediate is higher in energy than this intermediate. The rate of the reaction depends on the activation energy. And so the rate of the reaction forming the tertiary carbocation will be a lot faster than the reaction forming a primary carbocation. And so most of the molecules are going to go through the tertiary carbocation, leading to this product. Finally, let's consider whether our proposed mechanism can account for this product. If we think about the mechanism, our alkene is going to share electrons with a proton, forming this carbocation. From here, if the Br minus shares its electrons with this carbon, that is going to lead to this product, which is what we see here. However, let's write this out in a little more detail. Here we have one hydrogen. Here we have just one hydrogen, and here we have a CH3. So this carbon is our carbocation, and this is a secondary carbocation. If this methyl group took its electrons and moved over here, well, we would still end up with a secondary carbocation. So that's not going to happen because there's no advantage. It has to spend energy to get no advantage. So that won't happen. But if this hydrogen took its electrons and moved them over here, what does that give us? So imagine this hydrogen with its electrons shared them over here. So we still have our CH3, C, CH3, CH, CH3, but now this other hydrogen is connected. And that leaves this carbon as a carbocation. Now we have a tertiary carbocation. If bromine adds to this rearranged carbocation, then what does that give us? Here's our CH3, C, CH3, CH2, CH3, and here is bromine. In other words, that is this product. So because the proposed mechanism proceeds through a carbocation, then it makes sense that a carbocation rearrangement could occur, leading to this product. And keep in mind, it is the observation of this product that led scientists to postulate the presence of the carbocation intermediate, because the only way that you could get this is if there was a carbocation rearrangement, which would only happen if there was a carbocation to begin with. So this experimental evidence is consistent with the proposed mechanism. It supports the proposed mechanism. So the different experimental data that we mentioned are all consistent with the proposed mechanism. So although we can't prove that mechanism, it is widely accepted for most types of electrophilic addition reactions.